the chance to interrogate the organizers because it was a pleasure for me to be here in Istanbul. I really liked the city. I had a great time, and I hope that you also enjoyed the school. I think I want to thank the students that make the school so lively and interactive. So I hope that this last lecture will be somehow useful because we are going to see a very important result in theoretical physics, which is the work of Seiberg-Witten. And this is famous work, and we basically try. The idea is that we'll see the solution of the theory that we introduced in the previous lecture, which is the n=2 theory with S equal to the H group. So before starting, just let me remind you what we thought last time. So we discussed the n=2 theory with H group S2 in 4 dimensions, and we wrote the effective action. Actually, we'll start with the pure S2 theory. This theory, the n=2 theory, we obtained by putting together two multiplets of the n=1 theory. We took the current multiplet, that was the thing that I call the multiplet psi, that contained as a physical degrees of freedom complex scalar and a premium psi. And then we also put another, these are n=1 supermultiplet. We also the vector multiplet that here enters through this superfield W that we define. So if we write this Lagrangian in component, it will look okay, so this is the way the Lagrangian looks like once it's in a component, and let me remind you that we chose the normalization such that the kinetic term for the gauge genus and that is in the n=1 vector multiplet is the same as the one of the frame side that enters in the current multiplet. So in this way we basically enhance the n=1 supersymmetry to an n=2 supersymmetry. So it was a matter of choosing appropriately the normalization and putting all the fields in the adjoint representation. So here, all the fields are in the adjoint of the super. And we also didn't add superpotential for the chiral fields. So in this way, we got a formula that is manifestly supersymmetric with n=2. And then we also got rid here in this expression of the auxiliary field, and because we solved the equation of motion and we plugged that as a function of z, so this is what we call the scalar potential.
So there is a derivative on the side.
Which
you
side?
forgot the derivative, I think, on the side.
On that side, yes. Good. Very good. So this is where we got by putting together these n equal 1 multiple to write down an n equal 2 supersymmetric Lagrangian, and then we also discussed briefly how to generalize this effective action to this action in Lagrangian to a generic effective action, which is still manifestly invariant under n equal 2. And basically, what we discovered is that we could do that by simply introducing the prepotential. Let me try to use the notation. So here I'm just considering n equal to U1 theory, because again this is the effective theory that we want to discuss. So here we introduce this function f that I call the homomorphic prepotential. The idea is that this theory, the U1 equal to effective action, for us appeared because we were starting from this n equal to theory and studying the vacuum of this theory, and we realized that to be in a supersymmetric vacuum, so with zero energy, we had to find a way to get this scalar potential equal to 0. So we choose Z proportional to A sigma 3, the depth in the vacuum of the scalar free proportional to sigma 3 with half, and A is a complex scalar. So if we disjoint this part, this object, the vector, the scalar potential is 0. So in this way, we decided to do perturbation theory in a supersymmetric vacuum, but because of this depth of the scalar, we had the Higgs mechanism that was breaking our SU2 to U1. Okay, this Higgs mechanism is due to the depth of the scalar Z, and we argue that the thing to do here would be to integrate out the massive degrees of freedom that we were due to this Higgs mechanism. So basically, we expect to have a U1 theory for the remaining light degrees of freedom that were in the direction 3. So in general, to write down this effective action is an extremely complicated procedure because one should do really the Wilsonian approach and compute lots of Feynman diagram starting from this microscopic theory. But then we observe that we are particularly lucky because in this process of breaking SU2 to U1, we are not destroying the supersymmetry. So we are still dealing with an M2 theory. So our low energy effective action has a form that is completely dictated by n equal to supersymmetry, and we have only to write it for an abelian H group U1, which is the surviving one. So this is the form of our low energy effective action after doing this Wilsonian procedure, and all what we had to do is to try to find the form of this function f, the potential that is encoding all the mess of doing this effective action procedure. So this is where we got at a certain point. We saw something more. We also saw how using some arguments from other symmetries of the theory, we discussed the U1 asymmetry that is anomalous. We got an argument that for which we understood that f of z, the homomorphic potential, is just given by this expression. So this we got from this equation. So this is basically an anomaly computation, and this is what is usually called the one-loop holomorphic nonpotential. So this result is actually one-loop exact, so there are no other correction in perturbation theory. So this is the result that we have if we do perturbation theory. So imagine that if you really start from this N equal to S2 theory and you do the Wilsonian approach, you would get on a U1 theory, N equal to, and F, you would really discover that it has this form. Here, there are no other corrections. So this is the exact result for the low energy effective action in perturbation theory. So this is where we got last time. And so now what I want to discuss is that there are, in fact, some corrections to this prepotential. So beyond the perturbative correction, one can expect the presence of some terms that are non-perturbative. So generically, you would expect that some non-perturbative contribution will have, this form, where k is an integer, is something like 1 over g. This is the form of the instance that you would expect. So now if you just use the fact that we call, so the second derivative of the prepotential is basically giving us, evaluated in A, is giving us tau effective of A, and using that tau effective of A is basically 1 over g of A plus the angle with some normalization. You can express g of A as a function of A, considering that f of A has this logarithmic form. So if you plug the g dependence, the g as a function of A here, you will discover that the non-perturbative contribution, they are actually, they show up in this form. So this is the kind of non-perturbative correction. You can prove this as a homework. So you prove that non-perturbative correction, they actually are power of lambda over A once you use the running of the coupling as a function of A. Okay, so let me So in general, the form that you would expect for the full the potential evaluated in A, which is for us is the value of the scalar. So imagine when you are doing the Wilsonian reduction, you integrate from A, which is the energy scale set by the value of the scalar, to some lambda bar, which is the cutoff, some high energy scale. This lambda is not this lambda, so let's distinguish. So if you write down the generic form of the potential, this would be the one loop part, which is also the full story perturbation theory, plus some tower of correction. So f of k, they are just some numbers, and they appear in this expansion. So the problem that Seiberg-Witten wanted to attack was how to find this infinite tower of non-perturbative correction. Okay? So this is what we are going to do today. So last time we saw that this is just coming from n equal to supersymmetry and anomalies, and this is the result of this exact perturbation theory. And today we'll show how to fix also all these coefficients at k. Okay, so this is an infinite tower of terms that we have to find a way to fix. Okay, so the solution of this problem will be first of all to try to use the fact that this function f of a is holomorphic. This morning we commented how much is important the concept of holomorphy, and we'll go and explore this very much. And to do that, we will, at the beginning, make the problem even more complicated because we'll produce other expansion with other coefficients. So at a certain point, we'll get to a point where we have a problem which looks worse than the one that we had at the beginning, but then we'll have some global compatibility condition that will basically fix all the coefficients. Okay, so first of all, I want to introduce a quantity which is, well, we have already seen it, but it's just the derivative of f of a with respect to a, and let me define this as a dual. It will be clear later why I call it a dual. So I'm just differentiating the perturbative part. Okay, so, right. So this is the behavior of this function, a dual, when a is big. I'm just forgetting about the non-perturbative correction. Right now I will just focus on the perturbative correction. And so now we need to express, we want to think about this a dual as a function of the parameter u, as well as a as a function of u. Now u we introduced last time, and I remind you that when we gave the vev to z equal to a squared half sigma 3, we introduced another object which was the trace of z squared, the vev, that I call u. Now these two objects, when u and a are big, they are simply related like that. But this is true only in a certain region of our moduli space. So the moduli space will be basically the manifold of the boundary of the theory, and I'm choosing this coordinate u to parameterize it. So you have to imagine that you have somewhere space that I'm calling M, which is the moduli space of the vacuum of our theory, which is parameterized by u. So you can imagine this as the defined complex plane of u. And there will be a point where u is equal to infinity, where u is more or less behaving as a squared. And now we are looking at around that region. So we are interested in the region where a is large and u is large, so they are more or less this way. Okay, so at this point, the expansion of a dual will look like that, and a will look like square root of 2u. Very good. So this is the expansion that u around infinity. Now, if you look at these two objects, a dual and a.
Sorry.
Yes, please.
Do you have a u square or u in the trace z square?
It's u.
How's your?
It's u.
And z is a square?
Z? No, sorry. This is z. Thank you. Okay, so right, we now we look at these two objects, and you see that as functions of u, they have branch cuts. So let's look at this a. This is square root of u, so you know that in the complex plane, the square root will have a branch cut, and when you cross the branch cut, you change sign. The same way, this a dual has some, as a function of u, will have some square root coming from expressing a as a function of u, as well as some branch cuts coming from the log. So you know that in the complex plane, when you cross the branch cut of the log, you get phase shift of 2 pi I. You know this. So we want to see what happens if you just take a vector made by the two variable AU and A that I will now be calling periods, or it will be clear later, and I want to study what happens when we go around the point U infinity in the complex plane, and we know that there will be somehow a branch cut because we have this behavior with square root and logs. Okay? So this can be just argued by looking at this expression at large U, that this can be obtained by this method here. So you can easily understand this transformation. This is just taking account. So you see that this minus is just the sign flip of the square root when I'm going around the branch cut, and this 2 that is giving a combination of AU and A is coming from this log. Okay? So this object that is something that's called a monotony matrix because it's taking account the effect of rotation around this point of infinity, so I'm calling this M infinity. So this is the monotony matrix. Okay? This is here. So good. So we know that this vector of field. So first of all, notice that what I'm discussing now is just starting from the perturbative part. I'm not considering a whole new perturbative part. So this is something that some sort of analysis that I could do without knowing anything about perturbative contribution, which is the thing that I want to describe. So I'm just taking the perturbative part and just observing the behavior at infinity. Now, the very fact that we know that there are some singularities in the complex plane means that there is some branch cut. So what we would expect is that this branch cut will end somewhere else. So we expect to have another point in the modular space, MU, where this branch cut ends. So the natural thing that people were expecting, the natural intuition would be that the other singular point is 0. Okay? So I'm warning you, this is going to be wrong, but this is just the thing that you would expect is the following. So you would expect that since you have this relation, when U is 0, A is 0. Now, if A is 0, you are not actually giving a bed to your scalar field, so you are not having the Higgs mechanism, so you are not doing any of the things that we are discussing now, like looking at the U1 theory that you obtain after the Wilsonian renormalization. So the intuition was exactly that there is another singularity, which is 0, and in 0 you have indeed there is no Higgs mechanism. Now, both these assumptions are wrong, because the first thing that is wrong is that this relation that U equal to 0 implies A equal to 0 is wrong, because this behavior that U is more or less going like A squared is only true at large U. So only in this region there is this relation between A and U. So if I say U equal to 0, I'm not implying A equal to 0. So these are two distinct points. So now I'll try to give you an argument why U cannot be a singularity, and then we will see why A cannot be 0, and then we'll discover the solution. So now I'll try to explain you why U is not 0. Okay, sorry. Why U equal to 0 is not singular point. So the argument that Seiberg-Witten give for this is more or less working like that. So imagine that so U is another singular point, so you will have that A squared at this point would be a global coordinate, and then you will have that A is really everywhere equal to square root of 2U, and AU will be able to write it as the perturbative part plus some function which would be, in this case, an entire function of A. Now, if you have this condition and you compute dAUL in dA, which is just the second derivative of f with respect to A, which is just our effect coupling, you'll see that it will appear here the derivative of G with respect to A, but the derivative on an effect function will be harmonic function. Now, this function cannot have minimum, because this is a theorem in complex analysis. So this function either is constant or at a certain point will become negative. But we cannot have negative term in front of the negative coefficient in front of the kinetic term. So this is ruling out the possibility of having U as a singularity. Okay, so this is not possible. Another possibility would be that there is a singularity at a point US, finite point. And actually, now there is another argument that forbids isolated singularity, because actually we saw that we broke this U1 asymmetry to some discrete subgroup that was Z4. Actually, this Z4 is enhanced to ZA in the U plane. This is a bit tricky, but anyway, the residual symmetry of this U1 asymmetry is forcing to have paired singularity at finite point. So if you have a singularity at a point US, you will have also a singularity at the point minus US. Okay. So this is the already big improvement. Now this was absolutely non-trivial point. The understanding that in this model space there are 3 singular points and not 2 as one would expect. We now have still to understand what is going on at this singular point. So I told you that we cannot have U equals to 0, but one could still think that at this singular point you have A equals to 0. Meaning that at this singular point you have no Higgs mechanism. So this is where our story would crack, because we don't have any web in the scalar field. Now, also this possibility that A could be 0 at U equal to plus or minus US is ruled out by some argument. And the argument now is that if you if you are in this situation, you will have massless gauge bosons. Okay, because no Higgs mechanism. And in presence of massless gauge bosons, you would not have, you would preserve conformal invariance, so you would not have this breaking of asymmetry, but that is that we observe at the perturbative level. So of course, I mean, this series of arguments is quite intricate, and it's really amazing that Seiberg-Witten managed to find all these physically motivated arguments to infer this very complicated situation. So the solution of Seiberg-Witten is precisely having understood that this model space has 3 singularities, and now the last thing that we want to do, that they did, is to describe what is going on at this 3 singular point. So we already described what happens at this in this member. Also here is where we did our perturbative analysis. So we know here we have the Higgs mechanism, and we are dealing with a theory which has very heavy particles with mass A, and this is the low energy effective action. We don't know what is going on here. We only know for the moment that there are no massless gauge bosons. So something else is going on at this singularity. So what is going on is that some particles that we integrated out in the procedure of writing down our effective action is becoming massless. So I mentioned to you yesterday that when you study a Wilsonian approach, you can write down an effective action for massless series, and there are no infrared singularities. The only problem you can have is that if some particle that you integrate out, some region in the model space is becoming massless. So the particles that now are becoming massless, they are not the gauge boson, so there must be something else. Okay. So before looking at this part, what I want to see, so do you understand so far what is the logic you want me to repeat? Is it clear? Because it's quite
Can you repeat the masses? Why do you have masses? Why one of those turn out to be masses?
Okay, so, right. So, let's see, quickly. So, we understood that if we just do our analysis that is in this region, U infinity, we got this expression for the potential. Now, this, just studying this object, actually its derivative, and also A as a function of U, we realize that there are some branch cut structure in this U plane. So here there is a singularity. So we have to see where is, at least the branch cut has to end somewhere, so there will be another singular point in the model space. So the natural thing that we would say is that you have the singularity at U equal to infinity, and there is another singularity at U equal to 0, and the branch cut is going from 3 to 0. So in 0, what you would expect is that U equal to 0, expect A equal to 0. Now if A is equal to 0, we are not giving any value to Z. So this fact that Z is given a value is what produce the Higgs mechanism, and you get mass for all the fields that we are trying to integrate out. Right? This part is from, okay. So, here we are giving mass to a field in the direction 3. So we have, our fields are actually, so Z in general will be expanded let's see, AI, sigma I. These are the Pauli matrices. So we chose to give a value only in the direction 3. So in the direction 3, this is true, basically this expansion you can do for all the fields that we have. There will be V mu, lambda, psi. So all these fields, they get mass through the Higgs mechanism in the direction 1 and 2. The direction 1 and 2 for all the fields are massive fields. You have a mass term in the Lagrangian. Now, so since you have a mass term in the Lagrangian, we can integrate them out and look at low energy effective action for the fields in the direction 3, which are psi 3, lambda 3, V mu 3, and also the scalar in the direction 3. So this, what we did, this n equal 1 low energy effective action is precisely written for the terms in the direction 3. So this is why it's a U1 theory. So this U1 theory has the form that I wrote, the effective action, with this prepotential. Now, this prepotential has the structure, and a possibility is that at point where U is equal to 0, you have problems, because indeed at this point you don't have mass terms for the fields in the direction 1 and 2. So the intuition will tell us that something is going wrong at U equal to 0. And precisely what is going wrong, we expect to have no Higgs mechanism. But this is not actually what is going on, because U cannot be a singular point for some argument. You can actually read better in the notes. And the other point is that you cannot have A equal to 0 also at other points, so you always have massless stage bosons. Massless stage bosons, meaning massless V mu in all the directions, they are not allowed.
So you say we have massive games?
We have massive games.
I understood the opposite.
There are no massless stages. This is what you would expect, but those are not the particles that are going massless here. Here there must be some other degrees of freedom in the theory that is going to become massless, because this is what is usually producing singularity in the low energy effective action. So this cannot be gauge boson, so we have to look elsewhere to find where are these particles that are going massless.
What is the argument against the massless gauge boson?
The massless gauge boson, you would have some infrared conformal invariance that would protect you against the breaking of this U1 asymmetry that is said you observe perturbatively. So, I must confess, this is a really, amazing intuition skills of Seiberg-Witten to construct the solution in this way. So these arguments, they are not at all obvious, but they do not be correct. Because the solution that we see is self-consistent, so the solution is correct. But constructing like that is really interesting.
And why would US implies minus US being also because of discrete strings, right?
So this is the surviving part of the U1 symmetry. There was a Z force.
So why not four different?
Okay, the mean. So infinity and zero, they are just basically mapped to themselves. So singularity of finite point, they come in pairs. You can discuss if you have more than two. So this is actually something that is not a theorem, but it has been proved that the solution, the monodromy problem that we're going to solve, has no solution if you have more points. This has been proved for 4 and 6, at least by hand, but there is not a complete proof. So this is, if you want, the minimal assumption compatible with all the constraints that you have. Okay? So now let's try to. Okay, so now we expect to have some singular, some particle going massless here, but we don't know exactly what are these particles. So again, very surprising observation by Seiberg-Witten is what are these particles going massless? Well, those are some collective excitation, but they are monopoles. So this is basically why at a certain point, last lecture, I was talking about the Doğuş-Polyakov monopole. This thing was probably look a bit weird to discuss that point, but I did that because now I want to mention basically this sort of slogan that appeared in this discussion, that in the presence of a compact U1 H group, which is what we have here, because we are now studying a U1 theory that is obtained by breaking. So here we are studying an S2 theory which is broken into one. So the fact that A is going to be still different from zero, and we are not going to have massless H boson. So the Higgs mechanism is there. So we always have a breaking of S2 to U1. Plus the fact of looking for finite energy configuration was implying this plus looking for finite energy configuration. This is what we discussed in the context of the Doğuş-Polyakov monopole. This was enough to imply this existence of monopoles, this excitation. Okay? So we saw that in a context that was not supersymmetric. Of course, what is going on here is the supersymmetric version of that mechanism, but at least the idea is the same. We are exactly in the same condition. We have a U1 compact H group, and we are looking for finite energy configuration. So we know that there are monopoles. So the idea of Seiberg-Witten is that the particles that are actually going massless at this point, there are some monopoles of the theory. Okay, so we should now try to describe a bit more these monopoles and to see how they, if we can write down an effective function also for the theory of monopoles that we have at this point. So this description, let me copy it here. So this is, now you should think of this solution as a solution that is valid only in a patch of the moduli space. It's not valid everywhere. So this, so far we are almost able to describe the theory in this region around U infinity, and we are, but we don't know still this part due to the non-perturbative effect. And we are trying now to find out what's going on here, but now we know that here there are some monopoles, so we want to study some theory of monopoles at this point. In the same way that at this point we study the theory of very heavy particles. Okay, so it's a point to make some comments about monopoles. Okay, so this is, I want to just sketch this computation that I don't have time to do because it's quite long, but it's not very complicated. So the thing that one can do is to compute the intercommutator of two supercharges as a function of their of currents. So this is quite a standard thing to do, but it's very long, and I'm doing it in the blackboard, but you will find it in the notes. So if you write it in terms of the currents, you find an expression like that. And also for the complex conjugate. This expression is very similar. Now, when we discuss monopoles, we also, at probably a certain point, wrote the electric charge and the magnetic charge of a monopole. And they took this form. So basically, if you remember that the intercommutator of two central charges gives, the central charge, this gives us an expression, simply substituting this here, gives us an expression for the central charge as a function of the electric and the magnetic charge of a monopole. So A and M are the electric and magnetic charge of a monopole configuration. Actually, if you have both electric and magnetic, this configuration are called dions. So there's a dionic configuration. So this is the Z that appears in the commutator of the intercommutator of Q alpha I and Q alpha J. Since here we are doing n equal 2, we have only two indices, so this is just 1, 2, Z. They are intercommutator to Z. Okay, so and Z for us has this expression in terms of the electric and the magnetic charge of a monopole configuration. And remember also when we represented the n equal 2, or actually the n equal 1 massive states, we found this condition that M, the mass of a state, has to be bigger or equal to the modulus of the central charge if we wanted to have a Hilbert space positive norm. And we also commented when this condition is satisfied, when the mass is equal to basically the central charge, we are at the BPS bound condition that imply basically that the number of degrees of freedom that you have in the massive multiplet is exactly the same that you have in the massless multiplet. This is also important for us because we started with a theory with a certain number of degrees of freedom here, and we were dealing with massless particles, so it could not be that we ended up with a theory with more degrees of freedom. And this is because being in a ultra short representation, because we are satisfying the BPS bound, we have the same number of degrees of freedom as a massless representation. Okay, so we have this important relation between the mass of this excitation, the central charge, as written in terms of the electric and magnetic charges, actually we can introduce tau, the Coulombic constant tau classical, that as a function of theta angle and of the coupling. So if you use this expression, Z, and also that Z will take the form of A and E, electric charge, and okay, we're almost there. So far I'm being completely at the classical level, so what enters is the classical coupling constant. Now if we allow to have this effective action story of integrating all massive degrees of freedom after this Higgs mechanism, will have to replace tau classical with tau effective, that we discuss is the second derivative of our holomorphic potential respect to A, which is also the dual in the A. So at the end of the day, what one finds is that the central charge, which is also related to the mass of these monopoles, can be written like that. This is the font of that. The mass of this particle, okay, is proportional to A and to A dual. So notice that if I want to consider a monopole will be an object that has n A equal to 0 and n equal to 1. So just one magnetic charge. So the mass of a monopole will just be proportional to A dual. So A can be generic, but there could be a point where A dual is 0. So since A dual will be proportional to the mass of the monopole, you understand that in this moduli space, I could be at this point US, where A dual is going to 0, but A is generic, so it would still be large. So the idea is that at this point US, and similarly to this point minus US, the particles that are going massless are these monopoles, or generically dions, that are their masses expressed in terms of A and A dual. Okay, so again, these particles are there in the theory because of an argument similar to the one that I gave you for the Polyakov monopole, because we have a U1 theory, and we are looking at finite energy configuration. So if you look back at the discussion we had at that time, you expect to have this monopole configuration. So this is the supersymmetric version of that problem, and here we are just studying the mass of this particle that can be written in terms of the central charge, and they are BPS particles. So the thing that we should do now is try to write down an effective action for these particles, for the monopoles, and try to see if they also can be described in terms of the function f in these points. So you want like 5 minutes breaks for doing that? Okay, so let's start for 5 minutes. Writing here an effective action in these regions, I want to introduce one more thing, one last thing, but this is useful thing to, which is the duality transformation. n equal to u1 fraction that I think I wrote many times, so I don't need to rewrite. There is symmetry that now we are going to show, which is the following. So let me introduce a field that I'm calling phi dual, that by definition is defined as phi prime phi, which is the derivative of holomorphic prepotential with respect to phi, and phi prime dual of phi, which I define to be equal to minus phi. So this basically means that phi dual of phi will be just phi of phi minus phi dual. So it's just a Lagrange transformation. So now it's easy to see that if we just look at the first term of the effective action, that is formed, if I just rewrite it in terms of this dual variable, it will just be invariant, and this is quite simple to show. So phi cross will be just phi prime dual cross dual. And now it's just a matter of integrating by part to show that this is just phi cross dual, phi prime dual, phi dual. So you see that at least this first part of the n equal 2u1 effective action is invariant, meaning that it takes the same form when written in the variables phi and f phi, and when written in terms of phi dual and f of phi dual. Okay? So we have to check also the other term in the effective action, the one involving the gauge part. This is a bit more complicated. So when we write the action, we have to integrate respect to V. So V is the superfield, is the vector superfield. So you see that now we are actually considering that these W's are these superfield that we introduced that contain inside F mu, and their lowest component is the gauge node, but these superfield W, they are actually expressed as a function of V, so they are not independent with respect to the superfield V. However, we use this form because it's more convenient to work with the W with respect to the V. So one could also think of writing down this integral as the integral in W, where now we are thinking W as in the independent variable, and also introduce a variable V dual, which is in this moment will be just some Lagrangian multiplier that is enforced in some constraint. So this is the same as there, and the constraint that we have to impose will be coming from that part. So basically, the integration in V dual will give rise to the Yankee identity. So I'm just writing this integral. But now one can think of doing first the integration with respect to the W. So then integrate first the W. So in this case, we'll be left with the dual exponential of you can, as a homework, you can check this. You will see that this field W dual alpha shows up, where W dual alpha will be defined as -1/4 d bar d alpha d dual, where d bar d, I remind you that is the auxiliary field that appears in the vector superfield. This is the bar, and the alpha is just the covariant derivative that we define. So you need, and this time is acting on V dual, while for W alpha that was acting on V. So basically, the idea here is that you start from the action for the gauge part of the n=2 theory, written in terms of the variable f, phi, and w's, and you end up with something that is written in terms of w duals that are defined in this way. You integrate in dv dual, and now you just have to use the definition of d dual and f dual that I gave you before to understand that phi dual double derivative is just minus d phi and d phi dual, which is nothing but 1 over second derivative of phi of f of phi. So, right, so this is what we call minus 1 over tau effective, and this is what I'm defining as tau dual effective. So 1 over f second phi, this is nothing but f second dual of f dual. So you see that basically after implementing this transformation, we are just exchanging all the variables with their dual. In particular, tau dual will be equal to 1 over tau. So this is the idea of the electromagnetic duality, that is something that is roughly equivalent to exchanging the coupling in 1 over the coupling. And you see these are the level of the action. Okay, so it's just a manipulation and implementing this Lejeune transformation, and you just implement in this way, and you see that the theory goes into itself, and the coupling goes in 1 over the coupling. Okay, so the reason why I did that is because these variables, dual variables, the idea is that you have that the good description of the theory where when the coupling is 1 over the coupling is actually a theory that is written in a new set of variables that are the dual variables. So it makes sense that if you go in a region where the coupling is very big because it's 1 over the coupling that is weak in another region, to have a good description of the theory, you have to use a new set of coordinates to describe it. And these are the dual fields. So this is exactly what we are going to see in our case, because we have seen that to describe the theory around the region where u is equal to infinity and where the coupling is small, because here the coupling here is small, you can see, because remember that tau at u infinity, which is equal to the second derivative of f, is going like log of a. So when a is big, tau is big, but tau is roughly 1 over g, so g is small. So in this region, the coupling is small, and I can have a good description in perturbation theory, and the good variable here are a and f of a. But now we are going to explore some region, like around this two singular point, where we expect to have coupling, not small coupling. So we are like expecting to have to change coordinates to describe the theory here. And this is precisely what we saw, because basically we discovered that at this point there are some particles that are the monopoles that have a mass given by a dual, and a dual is getting close to zero here. So a dual, when U is close to US, we expect that will behave as U minus US. So something that is getting to zero at this point. So in some sense, the idea is that while the good coordinate around the point U infinity is A, and if you want F of A, the good coordinate at the point, at the singular point US is a dual that now is small, and there will be another function F dual of a dual that we're going to describe now that will be giving the effective actions of the theory at this point. But the basic idea here is that if you change region in the model space, you expect that you have to change the coordinate to describe your theory. It's not just coordinates, in fact, it's just the degrees of freedom of the theory. They are different, because first we were talking about particles that are very heavy, and there are particles sitting in the chiral in the vector multiplet of n equal 2 theory, and now we are thinking of having some different particles which are these monopoles, and they will sit in other multiplets. They will sit in the hypermultiplet of the n equal 2 theory. So there are different degrees of freedom, and you need different coordinates to describe the theory. Okay. Okay, so basically, the idea is that if you want to describe a theory of monopoles, so we have to describe a theory of light monopoles. So light, again, we expect them to be light because their mass will be proportional to a dual. So we want this to become zero at this singular point. So we want to write down the effective action for a theory that is that contains these degrees of freedom. So that will be again an n equals theory. But now you have to consider these monopoles which will sit into hypermultiplet, and the way you couple hypermultiplet to the gauge field is the same as you would couple electrons. So it would be like a theory, electromagnetism with very light electrons. So this theory is not asymptotically free, and you know how to write the beta function already. So this theory is not asymptotically free, the beta function is positive, and this is some standard analysis that you do with this theory. The only information that you need is that you have to write down the beta function for electromagnetism with particles that this time they are not electrons, but they are these monopoles and they are light. So you know already the form of the beta function, and the beta function is actually related to, is giving us the coupling as a function of the energy scale mu, and the coupling is also related to tau dual that will be in this case defined like that. So this time there are no theta angle because it's a theory like electrodynamics. And you can write it like that. So, problem.
What is beta function?
Okay. So I thought that Chan had discussed this in the theory course. So this is basically, if you want, this is the definition of the beta function is a differential equation that is telling us how the gauge coupling depends on the energy scale. So if you solve this equation, you will find your G, dual, that I'm going to get as a function of mu, gives the dependence of the coupling respect to the energy scale. And you can write it just knowing what are the degrees of freedom or your theory. And now I'm telling you that these monopoles, they actually behave as if they were electrons. So like if I ask you to write these equations for electrons that are of very light mass. So this is something that you could do a priori without knowing anything about the solution. If somebody would tell you, look, the theory that lives here is a theory of supersymmetric monopoles in their light. So this you could do. So since I'm preserving against supersymmetry, I know that the form of the effective action is the same that I've been writing many times. And again, that the only non-trivial information is encoded in the prepotential. And the prepotential has the property that its second derivative, dual, because now I'm putting this index dual to specify that I'm discussing another region where I think that the good coordinates are the dual ones. So by definition, for me, the effective coupling as a function of the energy scale that now is a dual is the second derivative of the prepotential. So just knowing the beta function that I can write down because I make the guess that there are monopoles being in like relevant degrees of freedom there, I can write down the form of the perturbative part of the prepotential. This is simply solving this equation and using this definition of dual with the scale here, mu being given by a dual. Okay, so if you do that, basically discover just through this equation, you just discover that tau dual is just more like minus 1 over p log of a dual. So again, you have a logarithmic piece in your phi dual in the function f. So f dual here will behave like minus I over p log of the dual. So notice that now here there is a minus, and the difference is that this theory here has a negative beta function because it's asymptotically free, while this theory is not. But this is something that I could do only because I'm making the assumption that here I have this theory of monopoles. So this fixes this sign, and again I'm left with some thing that I don't know, which is I will expect to have here as well some tower of non-perturbative correction also here that I don't know. So in this sense, I'm making the problem even more complicated because I started trying to fix this coefficient fk, and I realized in fact that my solution contains another theory in a different region of the multispace, where again I'm able to find what is the perturbative part of the prepotential, but I have no idea about these non-perturbative terms. Here actually. So here, at this other point, you have similar discussion where this time you don't have. So here you have a theory of monopoles, meaning that you have object with, this is the electric charge and M is the magnetic charge. They have charge 0, 1, so 0 electric charge and 1 magnetic charge. You remember first I described the central charge, which is equal to the mass for these BPS states that are called ions, and they have two charges, the electric charge and the magnetic charge. And if I'm calling something a monopole, it's something which has electric charge 0 and magnetic charge 1. So the situation at this other point in the model space is similar. You will have here another theory, where in this case you will have not monopoles getting masses, but some other doubles. I think something like particle with this charge going masses. And again, you can write down the beta function and write also here the form of the potential. So the situation now is more or less settled. I mean, one can know making the assumption of what are the relevant degrees of freedom, one can write down the perturbative part of the prepotential in each patch of the model space. But the question is that how are we going to match to find this tower of non-perturbative coefficient? So this looks again a problem that is worse than the initial one, where we had only one set of non-perturbative terms. Now we have 3 in each region, but now we'll see that there is some consistent solution that fixes all these towers, these infinite towers. Okay? But so far, this very complicated analysis is basically done only on the basis of one loop computation in perturbation theory. So we are only in the information that we could just obtain from perturbative analysis were these logarithmic pieces in every patch. Okay, so you remember that at a certain point we wrote down the monodromy matrix, which is basically the way the period A and the period A dual as regarded as a function of U behave when you go around the point U infinity, and we wrote the matrix that we call M infinity. And because of that singularity, we were expecting to have more singularity, and then we found these two. Well, now we know what is going on at these two singular points, and we can do the same kind of analysis. We can study the monodromy when we go around this singular point US. So how do we do that? So if we focus around the region US, basically we know already that we want to have a dual behaving like U minus US times some constant, because we want some, remember, is the mass of the monopole, and we want the mass going to 0 at that point, so this is a good parameterization. You could choose other one maybe with some power, but you can show the argument to show that indeed that this is the right behavior, and then you can also put this together with the other you can put this together with the other periods, which will be EA dual EA, which would be just the derivative of this F dual. This will be the second derivative of F dual with respect to A dual square, A square. So this will be just some log with a minus A dual over lambda. So now you can write down the monodromy, and you have here basically this object produces no monodromy, so we have only monodromy coming from this log, and you can define a monodromy matrix around the point US, and we'll take this simple form. And first we found this monodromy and M infinity. So these two matrices are telling us how the vector made by the two components, A dual and A, behaves when you go around this singularity at this point, M infinity, and at this point, M US. Actually, there are some consistency conditions that tell us that if we also introduce the monodromy at the point minus US, these three matrices, they have to multiply to 1. Okay? So, just to recap, so we managed just by purely perturbative argument to compute the perturbative piece for the prepotential in the three regions of the moduli space around the three singularities. Just looking at these perturbative parts, we are able to study the monodromies around the singular points, and we end up with three sets of matrices. Now, the last part that we will describe is how, just knowing these three monodromy matrices, we can write down some differential equation whose solution will contain also all this tower of coefficients. Basically, the consistency requirement is that this way of covering the moduli space of solution with patches with this coordinate has to be somehow consistent, and this is, if you want, is the consistency condition that the monodromy have to multiply to 1. So this condition will be that you can just obtain from perturbative analysis will be enough to fix also all the non-perturbative contribution. Is at least clear the idea? It's a marathon, but we are there. So one more comment is that, so what is really remarkable is that you start describing a theory in a region where you could do perturbation theory, that is when the coupling is weak, and this theory was a theory that contained certain degrees of freedom, which were basically the one contained in the n equal to vector multiplet, but then you discover that if you want to describe the theory in other region in the model space of solution, you have to consider other degrees of freedom of the theory that were not in the Lagrange that you considered at the beginning, because now we have seen that to describe what is going on here, we have to talk about monopoles that sits in the hypermultiplet. So some new degrees of freedom just begin when you try to describe this theory at other region in the model space. So, and what you have to do is if you want some very small effort from in perturbation theory to find the perturbative correction in all these regions and to get this consistency condition that will be enough to fix also the theory at a non-perturbative level. Of course, what is really non-trivial is to make the guess that here you have to change theory and to study monopoles instead of the original degrees of freedom. Okay, now we'll just write down the final solution. So the idea to solve this monodromy problem comes from the theory of differential equations. So a problem that will be familiar is that if you study, for example, Schrödinger equation, and you consider a periodic potential, you know that if you find the solution of your differential equation, so the solution evaluated at x and the one evaluated at x plus 2 pi I, they should be related. with some constant matrix. This is just a statement that the solution at point x will be just a linear combination of the solution at point x plus 2pi. This comes because I'm supposed to consider a periodic potential. Okay, so the idea is that this vector solution is written by a transformation that can be implemented by matrix with constant coefficient M. So this is very much similar to what we are going to now. So now we want to study a differential equation with complex coordinate. So we'll have potential V, and we'll have a function Z. Now we require that this potential V will be some meromorphic functions. So meromorphic means that can have some singularities, but they cannot be branch cuts or poles. So this requirement, the fact that this function is meromorphic, this potential is meromorphic, implies that if you solve this differential equation, then the solution that what happens to this vector when you go around, say that z0 is one of the poles of this function, imagine something like v only like z minus z0 to some power. So you expect that when you go around these singularities in this potential is meromorphic, you want to recover your solution by 1, by 2 in Z, and you want that this transformation is implemented by some matrix that I'm calling the monodromy matrix. So this matrix is really acting on our solution at the point Z and transforming it as the effect of going around this singularity. So now you understand more or less the idea that I'm trying to implement. We have, out of this Seiberg-Witten theory, we came up with a problem where you have three monodromy matrices, M infinity, M US, and M minus US, and we would like to find a potential V with three singularities such that the action at the three singularity is given respectively by M infinity, M US, and M minus US. If we manage to rephrase our monodromy problem in the problem of solving a differential equation with a right potential such that the monodromy that appears are the one that we obtain from Seiberg-Witten solution, then we would expect that these two, the solution, psi1, psi2, could be related to our period A dual and A. Okay, so that's the philosophy. So we have to solve a problem of finding these periods, and we came up with three matrices from the Seiberg-Witten theory. Now, a way to relate monodromy matrices to periods is in the context of differential equations. So what we should do is to make a guess of a vector of a potential V with some singularities such that the action of the monodromy around those singularities is implemented by three monodromy matrices that they are the one that we obtain from the Seiberg-Witten analysis. Okay, so the general guess that you can make for the potential V of Z will be something like that. So here, lambda 1, lambda 2, and lambda 3, they are just coefficients that you want to choose so that there will be 3 singular points in the solution of this differential equation. That will be 1, minus 1, and infinity. So that you want to choose this coefficient in such a way that monodromy at this point will be given by m infinity at infinity, and plus and minus n at 1 and minus 1 will be the monodromy at the point n us and n minus us. Actually, us is just, you can fix to 1. You can just choose to scale it to 1. So, okay, one can do that, and the solution is that one ends up with fixing precisely this coefficient. And the idea is that there is a good choice of this coefficient, that if the right logarithmic behavior for the solution, so the good choice will be a very simple one. So you can understand that this is the right solution by looking at the solution around z around infinity will fix the coefficient 3 equal to 0, and if you look at the solution around z equal to 1, you will get another condition that is lambda 2 equal to 1, and z equal to minus 1, you'll see that lambda 1 is to be 1. So this is basically just trying to reproduce as a solution of the differential equation the logarithmic behavior that we know from perturbation theory. This helps us to fix these coefficients. Okay, so at this point, basically we are done because we know the differential equation that we have to solve. So once you choose v of z of this form, this differential equation becomes a very familiar one, which is just a hypergeometric differential equation. So you can solve it for psi1 and psi2 that will be related then to our A dual and A of u. So the form will be, so this is the generic form in which you write down the solution of a hypergeometric equation. Okay, so this is the celebrated Seiberg-Witten solution, because if you take this two period and you expand them in powers of u, and then you can actually use this equation to invert u as a function of a, plug it back, you will have a dual as a function of a, but a dual is nothing but df in dA as a function of a. So you would find f of a, which is the prepotential that will contain a logarithmic piece, which is the perturbative piece that we obtain from the anomaly computation. And then you will have all the terms that are carrying the expansion of the hypergeometric equation that are the famous non-perturbative contribution that we were looking for. So these are all containing this hypergeometric equation. And the good thing is that if you this differential equation of this hypergeometric differential equation has actually many solutions, and you can choose linear independent solutions that are appropriate to describe each region in the model space. So basically, you remember that in some region we had this equation with this the point u equals to infinity, the point u equals to 1, and the point u equals to minus 1, and in each of these points we knew the form of the perturbative solution. So the idea is simply that one has to choose among the solution of this second order differential equation pair of independent solutions that have the right perturbative behavior in each of these parts, and then the rest of the term in this function will reconstruct the non-perturbative terms that we had at the beginning. So all the solution is basically contained in the form of a differential equation, which is the hypergeometric one, and contains all the tower of these non-perturbative contributions that were the thing that we wanted to conclude. So this is the result of the Seiberg-Witten analysis. I think we should stop here.